The equation of motion we had derived for a fluid element leads us to a very important principle which is very useful in practice, called Bernoullis principle, and today I am going to discuss that along with various other related matters. If you recall the equation of motion for a fluid element, so equation of motion of a fluid element was of the following kind. It made a statement about the rate of change of the velocity field of the fluid element, and it was of the form delta V over delta T plus V dot del on V was equal to, on the right hand side we had a combination of terms. We had a term which went like minus the gradient of the pressure divided by rho plus, so let us put everything inside, minus gradient of pressure over rho plus the potential out here, the potential energy per unit mass of the fluid was sitting here, plus a viscous term. And if you drop the viscosity of the fluid, assume that the viscosity is low enough that it can be dropped, there is inviscid flow, then this term we threw out and we had an equation of this kind. So this is not a trivial equation to solve, it is a complicated equation. As I have repeatedly emphasized, the fact that this V appears here and here makes it non-linear and very, very non-trivial to solve, even if you tell me what the pressure is and what the density is and so on at every point in space and time, you still have a difficult problem mathematically to solve this equation. That was the basic equation of a fluid element here. Now the way to derive this principle is as follows, is to first of all notice that this term here, it would be very gradient of phi, it would be useful if we could write this term here as the gradient of something or the other, but as a gradient of P divided by rho, and if the fluid is not, if it is incompressible, of course rho is a constant, it comes out, but otherwise you have a rho here and it is a non-trivial function possibly of the pressure, of the density and so on, of the velocity, etc. It is coupled to the velocity, but we can always write this term as a gradient term as follows in a very special instance, and that has to do with barotropic flow. But before I do that, let me come back and say a few things which were implicit in what I said earlier, but I did not say it explicitly. What is a streamline? Well, a streamline is just the field line of the velocity field. In other words, if at some instant of time the velocity vector at this point is in this direction, at this point is in this direction and so on, you join all these up and you get a portrait of the velocity field throughout the fluid at any given instant of time. Those are the streamlines. We have tacitly assumed that our flow is streamline flow, although I did not say it explicitly. This flow is assumed to be streamline flow in the sense that at every point it is assumed that there is a unique velocity field, a unique direction of the velocity and magnitude of the velocity at every point in the fluid at any given instant of time. Now these are the so called streamlines. The line of flow may actually be different in the sense that if you give me a certain point here, look at a certain point, if this whole flow changes as a function of time, in other words if V has an explicit dependence on time so that this derivative is not 0, then if at time t1 the velocity vector is along that direction, at a later time it could be along this or along this and so on. So the entire set of streamlines could actually change as a function of time. So this flow lines themselves could be different. So if you took a given parcel of fluid, it could be on one streamline at a given instant of time, and at a later instant it is on a different streamline, it moves this way and so on. So this could be the path of the parcel of fluid and it is not on any one given streamline. So the point is that if the flow is not steady, the streamlines and the lines of flow are different from each other. But if it is a steady flow, this pattern of the velocity field lines does not change with time. So, a steady flow corresponds to implies that delta V of RT over delta T is identically 0 at all points, no explicit dependence on time, and moreover streamlines and lines of flow are the same. They coincide with each other, and that is intuitively obvious, geometrically obvious here, that if the pattern does not change as a function of time, then we say the flow is steady. So, in the case of steady flow, we can drop this term here first. So, first assumption, let us look at steady flow. So, this goes away because steady flow. This goes away because I assumed that the fluid is inviscid, viscosity neglected. So, that gives you a little bit of simplification. Then we would like to know what this term looks like. In general, this term is quite complicated, but there is one kind of flow called barotropic flow, where it turns out that the pressure is some given function of the density, or reciprocally the density is some specified function of the pressure itself. Now, when does this happen? Consider, for example, the ideal gas, which we are going to study in some detail a little later. In that case, you know that PV equal to the number of moles times the gas constant times the absolute temperature here, right. We could rewrite this in many ways. We could write this in terms of the total number of particles times Boltzmann's constant times T, and therefore you can have you can write P is N over V K Boltzmann T, where this is the number of particles, this is the volume of the gas, and K Boltzmann is Boltzmann's constant. If I multiply top and bottom by the mass of a molecule, then this becomes Nm K Boltzmann T over V times m, but Nm over V is the total mass of the gas divided by the volume of the gas, and therefore is the mass density of the gas. So, here is an example. At a fixed temperature for an ideal gas, the pressure is directly proportional to the density and vice versa. So, this quantity here we can actually evaluate in this case, because rho becomes a function of P. So, for a general barotropic flow, implies that P equal to P of rho, or rho equal to rho of P. In other words, there is no other dependence. The density depends only on the pressure, all other variables are irrelevant. In that case, the temperature would have to be kept constant, and then of course you have exactly that situation. In fact, you have a relation which says P is proportional to rho directly, but here in general it is some nonlinear function, complicated function of rho. Another example, if the gas undergoes an adiabatic process, then PV to the power gamma equal to constant, as you are aware, and since V is proportional to 1 over the density for a given amount of gas, this says P is proportional to V to the power minus gamma, or density to the power gamma. So, that is another situation where you have a flow of this kind. Pressure or density is given as some function of the pressure. In that case, this term can actually be written down as a gradient of something or the other. So, let us see how that happens. Gradient of pressure divided by rho, if it is a function of pressure alone, can be written in the following way. If you have the gradient of some function of the pressure, this is equal to df P over dP times the gradient of the pressure. By gradient I mean derivatives with respect to x, y, z with those unit vectors put in here. So, this is of course equal to the gradient of an integral, indefinite integral dP over rho of P, because this quantity is an indefinite integral which is a function of p, and its derivative is precisely 1 over rho. So it is clear that by this rule the gradient of p over rho of p is the gradient of the indefinite integral dp over rho of p, and if you tell me p rho as a function of p, I can compute what this function is here in principle. So therefore under these assumptions of steady flow, inviscid flow, barotropic flow, we finally have the statement that v dot del on v on the right hand side becomes equal to minus the gradient of integral dp over rho of p plus phi, and that is it here. Next, let us take the dot product of both sides with respect to v, and therefore you have v dot this quantity equal to minus v dot the gradient of this scalar quantity. But look at what the left hand side is, and let us write it out explicitly. I do not want to use any vector identity, we can simplify this directly. Just a little bit of algebra, but it is instructive to see what happens. This quantity is a scalar operator because there is a dot product here. It involves derivatives and it acts on a vector to produce a vector, and you take the scalar product of that vector with this v. So this thing here should be simplified as follows. Let us write out v dot del on v is equal to vx delta over delta x plus vy delta over delta y plus vz delta over delta z acts on Ex on velocity, which is Vx Ex plus Vy Ey plus Vz Ez in this form, and there are 9 terms in this expansion, but they are fairly easy to write down. So let us write the first one down. This is going to be V dot del on V equal to, so pull the Ex out all the way to the left and you have Vx delta Vx over delta x plus Vy delta Vx over delta y plus Vz delta Vx over delta z. That takes care of differentiating this term here, these 3 derivatives acting on this term. The next term will be a Vy outside and an Ey. So we had a Vy plus Ey times this term, let me see if I have done this right. So you have a Vx, Vy, Vz, and then I am going to take this operator and act on that. So this is going to be a Vx delta Vy over delta x, sorry, Vy delta Vy over delta, got to do this properly. So I have Vx, what have I done? I differentiated Vx each time, plus Vy, that term is quite correct. So I have a Vx, sorry, I have a Vx delta Vy over delta x plus Vy, yeah, plus Vy delta Vy over delta y plus Vz delta Vy over delta z, sorry, so that is perfectly correct, plus Ez times So, we got this term here and it is Vx acting on this fellow here. So, it is Vx delta Vz over delta x plus Vy delta Vz over delta y plus Vz delta Vz over delta z. Yeah. So, those are the 9 terms here, and now add them up in this form here, this plus this etc., and what do we get? That is not the best way to add it up. Z. Oh yes, okay. Now let us dot this with V dot this here, yeah, so that is it. This is going to be Vx, of course, Vx Ex plus Vy Ey plus Vz Ez, and I use the fact that Ex dot Ex is 1, Ex dot Ey is 0, Ex dot Ez is 0, etc. So, dotting this is going to give me Ex dot Ex is 1 and it is multiplied by a Vx out here. Then the Ex dot Ey is 0, Ex dot Ez is 0. The Vy part of it is just going to produce a Vy here, and the Vz part of it is just going to produce a Vz here. That is it. Okay. And we are in good shape. So, we now have a formula which says V dot del on V is equal to, let us collect terms, and I collect this term and this term first, and notice that Vx is a common factor. So, this is Vx times delta over delta x, Vx squared over 2 plus Vy squared over 2 plus Vz squared over 2, because Vy delta Vy over delta x is half the derivative of Vy squared and similarly half the derivative of Vz squared. So, it is Vx times this plus Vy times delta over delta y, exactly the same quantity, Vx squared over 2 plus Vy squared over 2 plus Vz squared over 2 plus Vz delta over delta z, Vx squared over 2 plus Vy squared over 2 plus Vz squared over 2, which is of course equal to Vx delta over delta x V squared over 2, because that is the definition, the square of the magnitude of the velocity, plus Vy delta over delta y V squared over 2 plus Vz delta over delta z V squared over 2. But this looks like V dot the gradient of half V squared. So, we finally have our identity which says this quantity is equal to V dot del acting on V squared over 2. This is a scalar quantity, scalar operator acts on V squared over 2, which is what this quantity is here. Putting this back in our equation, we now have a statement which says that 0 equal to minus V dot the gradient of integral dp over rho of p plus phi, whatever be the potential per unit mass of this fluid, plus V squared over 2. I moved the thing this side from the left hand side to the right hand side and took the V dot outside, so it is V dot gradient of this. Now, what is the meaning of this statement here? It says that this scalar quantity, its gradient has no component along the vector V at any point, but the vector V at any point, its direction is actually the streamline's direction. So, it says that if you have a streamline like this At this point, this is the direction of the velocity v. And this statement says that this scalar function has no component, its gradient has no component along this direction at all. Therefore, it cannot change along this direction. This scalar function cannot change along this direction. If you recall, the gradient of a scalar gives me the rate of change of the scalar function along any direction whatsoever once I dot it with a unit vector of that direction. In this case, the velocity v is tangent to the streamlines, and it says that at every point this scalar function does not have any change as you move along this tangent. In other words, along a streamline, as you go bit by bit, increment by increment, this scalar quantity does not change. So this is Bernoullis' principle. It says that integral dp over rho of p plus phi plus v squared over 2 equal to constant on a streamline. This is Bernoullis' principle in a general form. It does not say it is the same constant on different streamlines. So if your fluid flows like this, and this is at the other streamline, these are the other streamlines, and that is the portrait of all the streamlines, this quantity is some constant C1 on this, some other constant C2 on this, some other constant C3 on this, and so on. In general, this is what happens, but otherwise on each given streamline we assert that this quantity is a constant. What are the assumptions that went into it? We said that the flow is inviscid, there is no viscosity, no dissipative forces. We said that the force, external force on it is conservative, comes from a potential, is a gradient of a potential. The flow is barotropic, so that you have the density as a function of the pressure of the fluid, and the flow is steady, so delta V over delta T is 0. Under those conditions, this quantity is constant on a streamline. Now we can immediately apply this to the case of an incompressible fluid. Then of course the rho comes out, and if the fluid is incompressible, this will immediately imply that P plus rho times phi plus 1/2 rho V squared equal to constant on a streamline. Rho is just a constant, and integral of dp gives you p, and that is it. This is the form in which you are usually familiar with this. In fact, if this comes from gravity and you have a flow which is under gravity, for instance, then this is written as rho gz in general. So p plus rho gz plus half rho v squared equal to constant. This is the form in which you usually learn in elementary treatments what the Bernoulli principle is. If it is a gas, for instance, then the density is extremely small, and in general it turns out that the effect of this pressure difference, this gravity potential difference is very, very negligible, and therefore if you neglect this, then it says P plus half rho V squared is constant, which is the form in which we see it in its most elementary form here. Incidentally, if this is a streamline and you have a pressure P1, a density rho 1 here, and a pressure P2 and a density rho 2 here, and a height h2, and this is at some height h1 above the ground level, then this equation here tells us that P1 plus rho 1 rho g h1 plus 1/2 rho V1 squared equal to P2 plus rho g h2 plus 1/2 rho V2 squared. The velocity is V1 here, this velocity speed is V1 here and V2 there, it tells you this. So it actually says that P1 minus P2 over rho, let us take rho, plus g times h1 minus h2 equal to 1/2 V2 squared minus V1 squared. So, the change in the kinetic energy, if you like, is equal to the work done on this fluid by this pressure head and the gravitational potential. So, the force of gravity and the pressure head together do work and change the kinetic energy of this fluid, and it is written in this form. So, this is the form in which Bernoullis principle is used very, very often. But we have a much more general relationship which actually says that when you have barotropic flow of a steady flow of a barotropic fluid under a conservative external force in the absence of viscosity, it is this quantity that is constant along any given streamline here. Next, I would like to introduce a slightly more subtle concept in fluid flow, and that has to do with circulation. This is not generally taught at an elementary level, but I want to do this because again we have already seen that fluid flow has offered us a very natural way of understanding certain operations like the gradient of a scalar, the flux of a vector field, which means the divergence of a vector field, the flux per unit volume. There is one more concept called the circulation of a vector field, and since it appears so often in various applications of vector analysis such as Maxwell's equations in electromagnetism, it is worth doing it here, and I intend to do that. Next we will discuss in very elementary terms the concept of the circulation of a vector of a fluid and what is meant by the curl of a vector of the velocity, because it has physical implications.